So in this lesson, we're going to start looking at Ampere's law and look at how does Ampere's law really help us in solving magnetic fields. And so if we go back to Ampere's law, it's very similar to Gauss's law for electric fields. And like we said, it is easier for lots of situations than the Biot-Savart law to determine the magnetic field. So let's look at why it isn't as complicated as it looks. Let's decode Ampere's law of what all these things say. So Ampere's law, first of all, remember it's very similar to Gauss's law. It looks like you have this crazy integral on the left side and something that's pretty easy on the right-hand side. So the integral b dot dl, this equation is what's called a line integral. What a line integral means is you're taking and you're integrating b times l, but you're going around a closed loop rather than a closed surface. So in Ampere's law, we generally talk about creating what's called an Amperian loop, which is a closed loop that you're going to do this line integral on. So a lot of times, if we choose our loop correctly, we've chosen a loop where magnetic field is constant. And so it can be rewritten this way, b times the line integral of dl. Now, if we think about what the line integral of dl really means, is if we take that and work that out, it really equals how long is that loop from one end of the loop to the other end of the loop. So if I have something like a circle, then the line integral of a circle is 2 pi r. This is very similar to the surface or the area integral that we used for, or the surface integral we used in Gauss's law, that when you do a surface integral dA, you basically get the surface area of a closed surface. In this case, you get the line of a closed, or the length of the closed path. So really, that left-hand side of the equation becomes b times whatever the path length of your loop is. The right-hand side of the the equation is dependent upon how much current gets enclosed by the loop that you've drawn. This is similar to how much charge gets enclosed by the surface. While the right-hand side looks like it's easy, multiply this number by this number, the right-hand side may be a place where you have to do an integral, particularly if you have something weird going on where you have like a bunch of current moving through like a large wire. That'd be kind of an odd situation. I'd have to really think about what type of situation where you'd have a current where you might need to integrate. So let's look at a long straight wire of current, and the current has I moving out of the page, and we're going to find the magnetic field at a distance r from that wire. Now, you maybe have played around with this and did this using Biot-Savart law. We'll see that Ampere's law is a lot easier. First thing to do is choose the path to do the line integral. This is what we call the Amperian loop, and the path I've chosen is a circular path around the wire. The reason why I've chosen a circular path is the magnetic field is going to move in circles around the wire, so the magnetic field is constant on this loop. Second step is determine the length of the path that's been chosen. The length is just the circumference of the circle, 2 pi r. Third step, add the enclosed current. The current enclosed by my loop is whatever the current in the wire is, I. Fourth step, solve for b. b equals mu naught I divided by 2 pi r. And then fifth step, use the right-hand rule to determine what direction the current's going to go, or the magnetic field's going to go. If the current's coming out of the page in this case, if you curl your hands, you find that the magnetic field is in a counterclockwise direction around that wire. So that's how you apply Ampere's law. Really, if you had done this using integration and Biot-Savart law, it probably would take you about 15 to 20 minutes to solve that out. Here, it took us literally like 30 seconds to solve what the magnetic field is from a long straight wire. What we'll do in the next lesson is we'll start to look at some applications of the Ampere's law and look at some situations that are pretty common scenarios that we come across.